All right, today we're going to talk about section 7.1, polar coordinates. Okay, double check. Okay, so basically polar coordinates and the polar coordinate system is just an alternative way to represent points and graphs and everything else. We're used to the rectangular coordinate system. The rectangular coordinate system is the one you've seen all your life, right? The XY coordinate system. And so in rectangular coordinates, we have these two number lines. One is the x-axis, one is the y-axis. 1, 2, -1, -2, etc., etc. Again, this is the one we've seen all our lives. Okay, we know how to plot points, we know how to graph things, we know how to do all those things in rectangular coordinates. And now we're going to learn how to do them in what's called the polar coordinate system. So the polar coordinate system is based on, and this is all on page 686 in your book. Okay, the polar coordinate system consists of a fixed point called the pole. So based on a fixed point called the pole, and they're going to use capital O to represent the pole. And you can kind of think about that, you can compare that to the origin in the rectangular coordinate system, because what we're going to learn is that we're going to be able to, just like we can plot points and graph things in rectangular, we're going to be able to plot points and graph things in polar. And we're going to learn how to convert from polar coordinates to rectangular coordinates and vice versa. And once we do, we're going to we'll be able to kind of superimpose maybe that polar coordinate system over this rectangular coordinate system. So again, when I say this polar coordinate system is based on a fixed point called the pole, we're going to call it O. It's going to coincide with what's the origin in the rectangular coordinate system. So it's based on a fixed point called the pole. We indicate that with O, and a ray called the polar axis. And a ray okay. All right, within point at the pole, okay. So I'm not gonna go through all that, make sure you read it. So basically, we'll identify a point P. Identify a point P as follows. So we've got the pole right here. And if we've got some point that P that lives in the plane, well, based on, again, it's going to be oriented with the pole kind of at the origin. Think about that as origin. There's my positive, what used to be the positive x-axis. I'm going to measure an angle theta, measured in a counterclockwise direction, just like we normally measure angles, right? And that's going to be, my point is going to be defined by the angle theta and the distance from the pole to that point P. So that's how we're going to define points, as ordered pairs r comma theta. This is how we define points in the polar coordinate system. Ordered pairs r comma theta. Back when we had rectangular coordinates, we had ordered pairs x comma y. In polar coordinates, we're going to have ordered pairs r comma theta. Okay? And again, we're going to get to the point where we can convert from a point xy to a point r theta, or from a point r theta to a point xy, okay? Now, again, every point can be defined as some r comma theta, where theta, again, is the angle measured from what used to be the positive x-axis in a counterclockwise direction. That's a positive angle theta. I could measure theta in a negative direction if I went clockwise, okay? And r is a direct distance from the pole to the point P, okay? So theta is greater than 0. Again, if I'm measuring counterclockwise, theta is less than 0 if I'm measuring clockwise, just like normal, okay? So now with all this in mind, let's look at a couple of examples. So example 1, plotting points in a polar coordinate system. So plot polar points. So A, the first point they give me is 3, 5 power 6. So again, r, theta. Every point in polar is some r, theta. So I want to plot the point 3, 5 power 6. Okay, 3, 5 power 6. So I have my pole right here, and I'm going to measure an angle of 5 power 6 from here. Okay, so 5 power 6 would be about right there. Okay, there's an angle 5 power 6. Now, what I've got to imagine is you've got to kind of imagine. Let me change this a little bit. So you've got to kind of imagine a set of concentric circles. That's a circle of radius 1. That would be a circle of radius 2. There would be a circle of radius 3, etc. So I made an angle of 5 power 6, and then I went 1, 2, 3 units out from that point, and there would be the point 3, 5 power 6. Okay? And again, you can kind of think about if you wanted to superimpose that old coordinate system, you could. Okay? But that would be the point 3, 5 power 6. Okay? Part B. Okay. So B, they want us to plot the point 5, negative 5 power, or 5, negative power over 4. 5, negative power 4. So again, draw your pole. Right? And I want to make an angle of negative power over 4. So there's an angle of negative power over 4. Okay? And again, I got to imagine circle of radius 1, circle of radius 2, circle of radius 3, circle of radius 4, and finally 5. Okay? So I make the angle of negative power over 4, and I start at the pole, and I go 1, 2, 3, 4, 5. So that would be the point 5, negative power over 4. Okay? C says 3.5, 3 pi. 3.5, 3 pi. Okay? Well, again, there's my pole. I make an angle of 3 pi. So again, one complete revolution is 2 pi. So if I start here and I go around once, that's 2 pi. Plus pi puts me right here. So there's an angle of 3 pi. Okay? And now I got to go 3.5. So again, imagine a circle of radius 1, circle of radius 2, 3, so 4, 3, 2, 1. So 3.5, I make the angle of 3 pi, and then I go out 1, 2, 3, 3.5, will put me right here. So there's the point 3.5, 3 pi. Okay. And finally, I'm going to call this D. Part D, they say negative 4, power 3. Negative 4, power 3. Okay. So again, draw your pole. There's my pole. I make an angle of power over 3. So an angle of power over 3, about right there. There's an angle of power over 3. Okay? Well, draw your concentric circles. Circle of radius 1. radius 2, 3, 4. Okay? So I made an angle of power 3, but since r is negative now, so instead of going out in a positive direction, 1, 2, 3, 4, and plotting that point, since r is negative, I make the angle of power 3, and I'll go in the opposite direction to account for that negative sign. So I'll go backwards, 1, 2, 3, 4. There's the point, negative 4 comma power 3. So when r is negative, I will go in the opposite direction. R is a directed distance. So if r is positive, we go in a positive direction along that terminal side of the angle. If r is negative, we'll go in a negative direction on the terminal side of that angle. Okay? Well, that's how we graph these points in polar coordinates. That's how we graph points in polar coordinates. Now, well, as you may imagine, so consider something like 1 comma power 2. Consider that point, 1 comma power 2. So there's 0. So power 2 would be here. So again, circle radius 1, circle radius 2. 1 comma power 2 is right here. Okay, 1 comma power 2 would be right there. Now we know how angles work. If I make a complete revolution, then I'm right back where I started at. So if I start out at 1 comma power 2 and I go around 2 pi more units, I'm back at the same point. So I claim that 1 comma add 2 pi 2 power 2. So 2 pi plus power 2. 2 pi is the same thing as 4 pi over 2 plus pi over 2. Well, that's 5 pi over 2. So I claim that that point lives right here too. Because now I'd start here and I make an angle of 5 pi over 2. All the way around is 4 pi over 2 or 2 pi, plus another pi over 2 makes 5 pi over 2. I go out 1 unit, I'm back right at that point again. So in rectangular coordinates, points were unique. If I plotted in the XY coordinate system, the point 2 comma 3, there's only one point. That is a unique representation. That point is represented in one way and one way only. But I see in these polar coordinates that a single point can have more than one representation. Because I can add multiples of 2 pi to this angle, or I can subtract multiples of 2 pi from that angle. So each point in rectangular has more in our polar. Every point in polar representation. So every point in the polar coordinate system has multiple representations. Okay? Every point in polar has multiple representations. Okay? We saw it right here. Okay? So what we're saying is r comma theta will be equal to r comma theta plus 2n pi. That's one way to write it. Okay? Because I can keep adding multiples of 2 pi to that angle and I'll just keep winding up at the same point. Okay? Now there's another way to get a second representation. I also claim that r theta is equal to negative r theta plus pi. So I can have other representations with r positive, and I claim I can have another representation of r theta with r negative. Okay? What do I mean by that? So let's test this one out on this problem right here. So r theta, I'm claiming is 1 comma pi over 2. So according to this formula, r theta is negative r, negative 1, right? Because r is 1. Theta was pi over 2, so theta plus pi, so that would be pi over 2 plus pi. So that's the same thing as negative 3 pi over 2. So let's see if that point coincides. Let's see if these 2 points truly do coincide. So If I said -1, 3 pi over 2, so I'll first make an angle of 3 pi over 2. Start here, and this pen does it right. We'll keep these back. So if I want to make an angle of 3 pi over 2, I'll start here at 0. I'll come around to here. So there's 3 pi over 2, right? But r is -1, so instead of going a positive 1 in the positive direction on the terminal side of 3 pi over 2, I go in the opposite direction and I go right here. So it is true that these 2 points lie at the same place. That's another representation. So this is what we need to know. For every point in polar, that point can be written a bunch of different ways with an r positive, because all I got to do is keep adding or subtracting multiples of 2 pi. Or I can rewrite any given point in polar coordinates as -r theta plus pi because of what we just saw. Okay? So we'll always be able to have multiple representations for any given point in polar. Oops, sorry.